Hello everybody. Today I will be talking about the OSI model more in depth. First we will start with layer 1 of the OSI model, the physical layer. The primary function of the physical layer is to transmit the raw bits of data over a communication channel. Bit conversion is the process by which data from the upper layers is converted into electrical, optical, or radio signals for suitable transmission. Next, the physical layer defines the topology of any given network, including how devices are connected. Some common physical topologies are star, ring, bus, and mesh configurations for both wired and wireless networks. The physical layer also defines the physical medium that information travels through. This can include twisted pair cables commonly used in Ethernet networks, coaxial cables often used for cable television and broadband internet. Fiber optic cables use light to transmit data, offering high bandwidth and long distance communication. And wireless antennas includes radio waves used in Wi-Fi and cellular networks. The following is what basic bits of information would look like traveling over each physical medium. The left would be an Ethernet cable and the right would be a Wi-Fi antenna. Now we will look at layer 2 of the OSI model, the data link layer. One of the many technologies you can find on layer 2 of the OSI model are NICs, or Network Interface Cards. The NIC serves as an interface between the computer and the network. It is the very hardware component that directly receives and transmits the data. Here is a NIC for a wired Ethernet connection using an RJ45 connector. On the right is a wireless NIC using antennas connected via a coaxial connector. These type of NICs plug into the PCIe slots on a computer, although most are integrated into the motherboard now. Another layer 2 technology is known as the switch. The layer 2 networking switch is responsible for transmitting frames intelligently using MAC address and MAC tables. Where a hub simply repeats a frame out of all ports except the port it came from, a switch only sends the frames out of the designated port that it was meant for. Hubs have widely been replaced since the invention of the switch, and it is rare to see one deployed in the real world. So how does a switch know where to send the frames to? The networking switch uses a memory table of MAC addresses to keep track of which port the frames originate from. When a device is plugged in, the device communicates its MAC address to the switch that the switch then stores to its table. This allows the switch to be able to send the frame only on the port it is destined for. As you can see in the anatomy of a frame, you have the recipient's MAC address first, the sender's MAC address followed after, the type of data, the data itself, and something known as the FCS, or the frame check sequence. Something that makes the data link layer special is that it's actually made up of 2 sublayers. The data link layer is made up of the following 2 layers: the logical link control and the media access control. Let's take a closer look at the logical link control. The logical link control handles error checking and correcting, flow control, and serves as the interface from the MAC layer to the network layer. The logical link control handles error checking and correcting with something called the frame check sequence, or the FCS. The FCS is added onto the data to verify that the information was received correctly. Using a process called the cyclical redundancy check, it provides a mathematical form of error detecting. The logical link control handles flow control by allowing 2 machines to transfer data at the highest compatible reliable speed. This ensures that one system does not overwhelm the other. The LLC serves as a logical interface by providing a standardized interface to interact with the MAC layer and the network layer to allow multiple protocols to be used through the same physical medium. Next we have the media access control. The responsibilities of the media access control layer is assigning MAC addresses, encapsulating frames, and performing collision detection. A MAC address is a unique 48-bit long code represented in hexadecimal. Every network interface card is assigned one by the manufacturer. Frame encapsulation happens by adding MAC header information, converting it to a frame for sending on the local network. Collision detection manages flow and collisions by use of the carrier sense multiple access with collision detection, or collision avoidance for Wi-Fi. Next we have Layer 3 of the OSI model. A main function of Layer 3 is IP addresses. IP addresses allow for interconnecting networks by allowing packet forwarding. IP addresses are made up of 32 bits and can be configured to be static or dynamic. The different types of IP addresses are public and private, with private having 3 different sets of number ranges defined by classes. Another technology used at Layer 3 is packet forwarding. When IP data is added to a frame, it is converted to a packet. Packet forwarding is the process a router performs to find the optimal path for a packet's destination. By using protocols such as Open Shortest Path First, packets are sure to be sent on time using the quickest route available. A router is a Layer 3 networking technology because it requires IP to function. The routing device is assigned an outward-facing public IP address and an internally facing private IP address. Similar to a switch's memory table, a router uses its routing table to find and define the best path for a packet. The following is a demonstration showing a frame being converted to a packet after the router adds IP information to it for sending over the internet. Then, the packet is converted back to a frame so that the receiving NIC may read it. Layer 4 of the OSI model is the transport layer. One of the functions of Layer 4 are ports. Ports allow packets or frames to be sent to the correct application running on the device. A port is a numerical identifier from any number between 1 and 65,536. An application binds to a port so that it can send and receive data while also allowing other applications to run using different ports. Another function of the transport layer is end-to-end communication. This layer is concerned with how data will be transmitted. Layer 4 provides reliable or unreliable transmission of data, usually in the forms of TCP or UDP for connection and connectionless data transmission, respectively. TCP will first establish a reliable connection using a three-way handshake and ensure each packet will arrive correct, intact, and in order. UDP does not perform error checking or any sort of way to verify if packets were received correctly. It simply sends it out without establishing a connection first. Segmentation and reassembly is the process of dividing large data into chunks that are more optimized to send over the internet. Each segment of data is marked with a sequence number to ensure data arrives orderly. The following animation demonstrates how a machine can open multiple logical ports to allow multiple applications to run and communicate over the internet. Next we have Layer 5, the session layer. The session is a logical connection between two machines. When two devices establish a connection, a session is created. Session management provides multiple commands and controls to manipulate a session. Another function of the session layer is synchronization. Synchronization allows for checkpoints to be made throughout a session. This allows data transfer to resume from last stored checkpoint to avoid resending all the data again if there is an unexpected disconnect. The session layer dictates how data will flow during a session. It does this by specifying half duplex that allows data to flow in both directions but not at the same time, and full duplex that allows data to flow in both directions at the same time. The following is a demonstration of session commands being used between two machines. The sixth layer of the OSI model is the presentation layer. A process that occurs here is something called character encoding. The presentation layer translates data from application-specific formats to a standardized format. For example, an application can generate data that takes the form of ASCII. The presentation layer then converts the ASCII characters to Unicode characters to ensure that the data is properly interpreted across different systems. Another function of the presentation layer is data compression. Data compression is an essential part of data transfer. Data compression is used to optimize bandwidth and speed. This reduces the amount of data that needs to be transmitted, making communication far more efficient. Encryption secures data using a mix of keys, ensuring that only the intended recipients can decrypt and read the data. Information is encrypted by using protocols such as SSL or TLS, which utilize a mix of public and private keys to encrypt the data before it is sent over the internet, protecting it from eavesdropping and tampering. The following is a demonstration to show how encryption is used to send information over the internet. First, you take a normal message, and after encryption, it is unreadable to anyone without the key. But with the proper key, you may open up the message and read it. Layer 7 of the OSI model is the application layer. The application layer serves as the user interface to the network. Examples include things like web browsers and email clients that allow users to interact with network resources. The application layer also defines how the data will be represented. The application layer is responsible for formatting data for an application. This may involve converting objects to JSON or XML and ensuring that the data is structured correctly for the receiving application or to be passed down to the lower layers. The application layer has a variety of protocols that are used to generate data. Protocols determine how the data will be transmitted and formatted. Protocols such as HTTP, FTP, and SMTP operate at the application layer but format data differently. Here is the application layer isolated from the remaining layers of the OSI model. The two main components here are the user input and the web browser. The following is an animation demonstrating the user input being converted to a suitable data format that can then be sent across the network and over the internet to a receiving machine.